Next is magnetism. Um, Actually, this week we'll be considering two chapters on magnetism. Chapter 27, that'll be this screencast, part one. And chapter 28, that'll be screencast part two. So we'll start with the magnetic field. Here's a little introduction. I suppose everyone has played with iron magnets and observed the surprising forces that they exert. Suppose you have two magnets, two little bar magnets. Each bar magnet has a north pole and a south pole. If the south poles are close together, you get repulsion. Or if the north poles are close together, you also get repulsion. So it's sort of like charges. Like charges repel. Like magnet poles repel. And since these south poles are closer together than the north poles, the net force will be a repulsion. On the other hand, the south pole is attracted to a north pole. So like in electricity, unlike charges attract, in magnetism, unlike poles attract. So this south pole is attracted to the north pole. It's repelled from the south pole, but it's closer to the north pole, and therefore there's a net attraction. Now, why do these forces occur? Certain materials can be magnetized like this. And the most common is iron. So this is called ferromagnetism. And that's the most strong kind of magnetism. But there are other kinds of magnetism as well. Paramagnetism and diamagnetism. But let's think about ferromagnets. Pieces of magnetized iron. Why do they exert these forces? Well, it's something in the atoms. There are only 3 elements that can be magnetized like this: iron, nickel, and cobalt. So it's an unusual thing. And it's something related to the atoms. And the underlying cause for magnetism is electric currents. So electric currents create magnetism. And we'll be studying that in more detail in part 2 of the screencast, or in chapter 28, magnetic fields from moving charges. For example, we'll see that if we have 2 current loops, oriented in one way, they repel each other. If the currents in these 2 loops of wire are in opposite directions, then there's repulsion. On the other hand, if the currents are in the same direction, then these 2 current loops will attract each other. So it depends on the relative orientation of the 2 loops. If I start with this where there's a repulsion, and I flip this loop over so that it's in the same, has the same direction of current as the one on the left, then it becomes attraction. So in the case of currents, like currents attract, and unlike currents repel. Now, a current loop has an associated magnetic field. And it's kind of like a positive charge on one side of the loop, a positive pole, a north pole on one side of the loop and a south pole on the other side of the loop. It's not quite that simple, but the magnetic field has this same form as if you had a north pole on one side of the loop and a south pole on the other side of the loop. Which sides? Well, it's given by the right-hand rule. If your fingers curl in the direction of the electric field, then your thumb points in the direction from the south pole to the north pole, effective for that current. So for this current, I would have a polarity to the right. On the other hand, if the current is in the other direction and I use the right-hand rule, I find the polarity is to the left. Here, both the polarities are equal. And then these polarities behave in the same way as bar magnets. All right, now does a bar magnet have any current? Well, it doesn't have any battery, it doesn't have any wires. What kind of current does it have? Yes, a bar magnet does have currents. They're in the atoms. An iron bar magnet is made out of current loops, which are called iron atoms. Now, a piece of iron is not always magnetized. You can have pieces of iron with no magnetic effects. But a piece of iron can be magnetized. And when a bar magnet is magnetized, the magnetic dipoles are all aligned in the same direction. So each atom has an effective current loop and an effective dipole moment, where by the right-hand rule, one side is the north pole side and one part is the south pole side. There aren't really any poles, there's just the current. There's just the current. But by the right-hand rule, you can associate the direction of the current with a polarity. Now, if all the atoms, or if the majority of the atoms in the bar magnet are pointing in the same direction, have the same polarity, that's what we call magnetized iron. And then the attractions and repulsions of those dipoles, which occur on the atomic scale, explain the attraction and repulsions of the bar magnet, which occurs on the macroscopic scale. So the reason there are forces between bar magnets is because there are forces between the aligned atomic dipoles. So magnetism originates in the currents which occur microscopically, that is to say, in atoms. Now, we're also going to find that macroscopic currents create magnetism. And for example, that's what happens in an electric motor. In an electric motor, you have coils of wire carrying current. And those coils of wire exert forces on other coils of wire, and so you get a motor. You have to drive the motor by sending a current through a loop of wire. So either macroscopic or microscopic currents create magnetism. But in the case of ferromagnetism, the forces between bars of iron, it's the macroscopic atomic currents. Now, the forces are not action at a distance. Remember, in the case of the force between charges, the force between charges is not action at a distance. It's caused by a force field, which we call the electric field. Well, the same is true in magnetism. The forces are not action at a distance. They're caused by a force field, which we call the magnetic field. And the notation for the magnetic field is always B. The notation for the electric field is E for electric. For some reason, the magnetic field is called B for magnetic. The idea that magnetism has a force field was first expressed by Michael Faraday, the great scientist of the early 19th century. He called it lines of force. And his idea was based on a famous demonstration that he developed. He took a bar magnet, put it underneath a glass plate, and sprinkled over the top of the glass plate iron filings, little pieces of iron that had been removed off the surface of an iron surface to make little tiny pieces of iron. And what happens is what's shown in this picture. You get curves where the iron filings, those little slivers of iron, those little splinters of iron, act like compass needles. The compass needle always aligns with the magnetic field. So those little splinters of iron become magnetized in the magnetic field of this bar magnet. When they're magnetized, they act like a compass needle. They line up with the direction of the magnetic field. So you see, I guess if this is a north pole and this is a south pole, there's a magnetic field, or sort of, well, I didn't draw it very well. Let's see if I can draw it a little better. It sort of comes out of the North Pole and goes around and goes into the South Pole. So that's the magnetic field, B. Faraday didn't call it the magnetic field. Faraday called it a line of force. You see, filling up this whole space, filling up this whole volume, there are lines of field, lines of force. It was James Clerk Maxwell, who lived at the same time as Faraday. He was a little younger than Faraday, but he took Faraday's idea of lines and force and put it in a mathematical form, and he called it the magnetic field. And his theory also included equations for the electric field. And in fact, Maxwell developed the field equations for electricity and magnetism that we still use today. Well, that's the magnetic field. How do we define it? How do we define it mathematically? I mean, this pictorial demonstration is interesting and potentially useful, but it's not mathematical. How do we define the mathematical function? Well, as we're going to see, the magnetic field exerts a force on moving charges. And that is the phenomenon that we'll use to define the magnetic field. In other words, there's a deep relationship between magnetic field and electric current. Magnetism is caused by electric currents. It actually works two ways. For one thing, electric currents create magnetic fields. So an electric current, whether it's a macroscopic current in a wire or a microscopic current in an atom, produces a magnetic field. That's the subject of chapter 28, part 2 of the screencast. The other way it works is that when a charged particle moves in a magnetic field, it experiences a force. So a magnetic field affects a current. That's where the force comes in. There's a force on the current. A current is a collection of moving charges, as we saw in the past couple of weeks. So current just means moving charges. If you have just one moving charge, just one particle moving around in the magnetic field, one charged particle with a velocity, it will experience a force. And here's the formula for the force. It's QV cross B. Q is the charge on that particle. You could think of this as a little test particle. B is the magnetic field, and X is the position of the particle. V is the velocity of the particle. F is the force acting on the particle. Well, there might be other forces acting on the particle, but this is the magnetic force acting on the particle. Sometimes called the Lorentz force, named for Hendrik Lorentz. So we have a magnetic field. It fills up a region of space. We have, let me put it a different color, a little charged particle. The charged particle is moving in some direction. It has to be moving in a direction that crosses B. So the magnetic field is pointing in one direction. The velocity is in a direction that crosses the magnetic field. In other words, it has to be in a direction which is not parallel to B. I'll review the cross product in a minute, but you probably remember, you've encountered cross products before. The cross product of two vectors that are in the same direction is zero. So in order to have a force, the velocity vector and the magnetic field vector have to be crossing, have to be in different directions. All right, now that's a charged particle. So that would be a particle, let's again use a different color, a particle with a charge Q. Now, what's a charged particle? Well, the subatomic particles are charged. And so where magnetism is most important is when you have subatomic particles moving with respect to a magnetic field. Now, a current in a wire is due to subatomic particles moving. We saw last week, or a couple weeks ago, that the electric current is due to the motion of electrons in the metal. That's the electric current in a wire. In a plasma, you could have electrons, positive ions, negative ions, but let's think about a wire. It has a current I. The current I consists of the coherent motion of electrons. Now, the force on the wire, the net force on the whole wire, will be integral I dl cross B. Where does that come from? Well, you see, the force on a single particle is QV cross B. And I is dq dt. So I times dl, a little length along the wire, will be dq dt, that's I, and dl will be v dt, that's the length along the wire for the particles that are moving in a time dt. They have a kind of an average velocity v. So you see the dt cancels. This is the amount of charge in that little length of wire times V. So I dl cross B is the charge times V cross B. So you see these two are the same, really. I mean, think about the units. Coulomb meters per second. Coulombs per second times meters. So they have the same units. They're just related by this differential relation. Now, of course, usually you don't have just a wire with a current in one direction. You really have to have a loop of wire. So you have a loop of wire in a magnetic field. Well, the current will go in all directions around the loop, and so the net force will be zero. So the net force on a loop of wire in a uniform magnetic field, if the magnetic field is a constant, will be zero. If you had a magnetic field on the right-hand side and no magnetic field on the left-hand side, then there would be a net force. It would be the force on this part of the wire. This part of the wire is not in a magnetic field, so it wouldn't experience a force. So there would be a net force. But if you have a uniform magnetic field where the field exists everywhere and the wire is just inside the field, there's no net force on the loop. But there is a net torque. And the torque is M cross B, where M is the dipole moment. And again, you have a cross product. So there'll be a force in one direction on one side of the wire, a force in the opposite direction on the other side of the wire. Well, you have two forces on an object separated by some distance in opposite directions. That's called a torque. So, this point is kind of microscopic. These are macroscopic statements. Now, we use that phenomenon of the force on a moving charge to define what is the magnetic field. The magnetic field is spread out through through a large volume of space. So B of x extends through a volume of space. B is a function of position. If you put a test charge Q at a point x and give it a little velocity v, then the force on Q will be QV cross B at x. So you have a probe. It's a charge with a velocity. That's a probe. You put it at the point x, you observe the force by observing the acceleration of the particle, and you can conclude the value of the magnetic field. So this is how we define the magnetic field as a force field. It defines the field for any point in the volume. I hope you're taking notes because you're going to need these equations. F is QV cross B. That's the force on a charge, force on a particle. Or F on a wire is the integral along the wire I dl cross B. And you'll have to use those equations to do some of the Lon Kappa problems. And also the equation for torque on a dipole moment. Now, to do calculations, you have to be able to calculate a cross product. I'm assuming that you've encountered the cross product, a topic in vector algebra, in a math course or maybe in a previous science course. what's the cross product? Let me review it quickly. If you're uncertain about the meaning of cross product in vector algebra, then I recommend you look it up. You could just use the internet, do a Google search. Type into Google cross product of vectors and do a search. Look for the Wikipedia page on the cross product of vectors, and you'll get all the information you need. You'll probably get more information than you need. But let me just give you a quick refresher course on the cross product of vectors. If you're given two vectors, A and B, then the cross product is a third vector, C. So A and B are vectors, and A cross B is a vector. Let's call it C. Geometrically, it's defined like this. If you have the vector A in some direction, some magnitude, you have the direction B in some direction, some magnitude, the angle theta between the two vectors, then C is perpendicular to the plane spanned by the two vectors. So if you have two vectors that cross, that defines a plane. And C is perpendicular to that plane. Now that gives you two possibilities. C can either be perpendicular upward or perpendicular downward. So which is it? Well, it's given by the right-hand rule. If the fingers of your right hand curl from A to B, then the thumb points in the direction of C. So, picture this little diagram here and let your fingers point in the direction of A and then curl around to the direction of B using your right hand. Your thumb will be pointing upward. So that's the direction of the vector. What about the magnitude? Well, the magnitude of C is AB sine theta. The magnitude of A times the magnitude of B times the sine of the angle between A and B. It's going to become very important to use the correct notation for vectors. A vector has to have an arrow over it. If you write V, that's not a vector. In order to make it a vector, you have to write an arrow over the symbol. And if you leave off the arrow, you'll make mistakes because you won't know the meaning of V. So here's C with a vector over it. It's an arrow. It's got a direction and a magnitude. Here's C without a vector over it. If I write a vector here, that's wrong. This is not a vector. What does it mean, C with no vector symbol, no arrow on top? It means the length of this vector. What's the meaning of A where there's no arrow on the top of it? Well, this equation doesn't make any sense. It says a scalar is equal to a vector. That doesn't make any sense. A with no arrow over the top of it means the length of the vector A. So C is the magnitude of C. And if you don't distinguish between C, the magnitude, and C, the vector, by putting an arrow over the letter, then you're bound to make mistakes. All right, so the length of C is AB sine theta. If theta is equal to 0, in other words, if the two vectors don't cross, then C doesn't have any length. It's a vector with no length. It's just the 0 vector. If the angle between A and B is 90 degrees, then the magnitude of C is just the magnitude of A times the magnitude of B. So cross product is a kind of multiplication. You multiply A times B. But it's not as simple as that. You multiply A times B and multiply by the sine of the angle between the two vectors. So that's the geometrical meaning of the cross product, and we'll often have to use that picture. But that's not really the normal way to calculate the cross product. To calculate a cross product, we need a kind of algebraic equation And it's actually given by, let me change the color here. It's given by these three equations, where I'm using Cartesian components of the vectors A and B. So A points in some direction. In Cartesian coordinates, it's AX, AY, AZ. B points in some other direction, has some other length. It has components BX, BY, BZ. CX is AYBZ minus AZBY. CY is AZBX minus AXBZ. CZ is AXBY minus AYBX. You see the three components all appear in each one of these equations. Here it's XYZ. Here it's YZX. Here it's ZXY. So these are sort of cyclic permutations. If I start with XYZ, then I move the X over here, I have YZX. That's this one. Now if I move the Y over here, I get ZXY. That's this one. Now the easy way to remember this set of three equations is to write this determinant. You could say C is a kind of effective determinant. We're not really doing matrix algebra here. We're just, for the purpose of memorizing these equations, we're just writing this as a determinant of IJK, AXAYZ, BXBYBZ. So you remember from high school how to calculate the determinant. It's I hat AYBZ minus AZBY. So the X component, the I hat component, is AYBZ minus AZBY, like here. The Y component is AZBX minus AXBZ, like here. The Z component is AXBY minus AYBX. So, this determinant is an easy way to remember how to calculate cross products. That works for Cartesian components. Now, sometimes we'll use polar coordinates, cylindrical coordinates, or spherical coordinates. And then this doesn't help you so much. But we'll see some examples of that. Well, I'll finish this part of the video by considering the motion of a particle in a magnetic field. Let's say you have a uniform magnetic field. So the magnetic field in this calculation, it's a constant as far as x is concerned. So if I write B of x, it's just some constant. Let's say, well, the way I have it drawn here, it's pointing in the z direction. So let's say it's B k hat. And B doesn't vary with position, so I'll just call this B0. So this would be a magnetic field pointing in the z direction, constant. It's same direction, same magnitude everywhere. That's a uniform magnetic field. That's what I mean by uniform. Constant. Constant in space. Well, for the next 3 weeks, we're only considering magnetic fields that do not depend on time. Later on, we'll consider magnetic fields that also depend on time. But for the moment, magnetic field only depends on position. And in this problem, it's constant everywhere in space. And now I have a charge Q, which has some velocity. Let's say I started off at this point with this velocity. So let's say I put this charge down right here, and I give it a little kick so it's moving off in this direction. How will it move? Well, it'll move on a circle. I'm not exerting any force on it after I give it a little kick. I give it a little kick to give it some velocity, but after that, I don't touch it. After that, it moves around on a circle. Now, you remember from mechanics, if a particle moves on a circle, there has to be a centripetal force. So there has to be a force directed towards the center of the circle, because circular motion has centripetal acceleration. So there has to be a centripetal force. Well, the only force acting on the particle is the magnetic force. So the magnetic force has to be towards the center of the circle. And the magnetic force is perpendicular to the velocity. Remember the cross product? You have, let's call this one B. Let's call this one A. Let's call this one C. I better remember these are vectors. And A cross B is C. C is perpendicular to the plane spanned by A and B. That means it's perpendicular to A, and it's perpendicular to B. A and B aren't perpendicular. A and B are separated. The angle between A and B is theta. But the angle between A and C is 90 degrees, and the angle between B and C is 90 degrees. Well, F is QV cross B. So F is perpendicular to B. B is in the Z direction. F has to be in the XY plane. And F is perpendicular to V. That gives me uniform circular motion, where F is the centripetal force. Here's how to remember it. The magnetic force on a moving charge is sideways. The direction is sideways. That is, it's perpendicular to the direction of motion. So the velocity is in this direction. The force is perpendicular to that. It's also perpendicular to the magnetic field. You know, I'm applying this general picture to this problem, where I have A is V, B is B, and V cross B is F. Well, I'm assuming that Q is positive. So I'm assuming this is a positive charge. If I have a little positive charge here and I kick it this direction, it'll go around the circle this way. What's that? Clockwise. If Q were negative, then the force would be in the opposite direction, and it would go around in a circle counterclockwise over here. All right, so the magnetic force is sideways. The magnetic force does no work. F dot ds is 0. ds is in the direction of the velocity. It's the displacement of the charge. It's the infinitesimal displacement of the charge. It's in the direction of the velocity. That's perpendicular to the force. So F dot ds is 0. Those two vectors are perpendicular. Now, you remember from mechanics, this is the work done. If the work done is 0, then the speed is constant. So as it moves around, the speed is constant because the magnetic field does no work on a moving charge. So the speed is constant, but of course the velocity is not constant because we have Newton's second law. M dv dt is qv cross b. As long as v and b are crossing, well, m dv dt is not 0. So v is not constant. In fact, this is the condition for uniform circular motion. The condition for uniform circular motion is that the speed is constant and the force is perpendicular to the velocity. All right, so on the long kappa assignment, there'll be a number of problems which involve motion of a charge on a circular arc. Now, there's another part to the video for this week which describes how the magnetic field is created by electric currents. So I haven't talked about that yet in this video. Watch part 2 of the screencast to see how a current I produces a magnetic field B. We know from part 1 how B affects I. It exerts a force on I. Now you have to do the other part of the interaction. You have to see how current creates B.